Hi everybody, welcome and thank you for joining us today. My name is Laura and myself, along with my colleagues Kyle Ledoux, Jimmy Zheng and Elizabeth Tackett are the creators of Pioneer. And Pioneer is a self-hosted feature flag management tool. So let's take a look at the topics that we're going to be covering today. And first, we'll be looking into what kind of problems does Pioneer solve? And this is going to involve looking at the problems that are associated when an organization wants to add new features into their deployed application. And then Jimmy is going to take us through some of the solutions to those problems, and he's going to introduce the concept of feature flags. Next, Elizabeth is going to introduce you to our application Pioneer. She's going to show you how a user can interact with our application, and she's going to take you through Pioneer's architecture. Then Kyle is going to give an insight into some of the technical decisions and engineering challenges that we faced while building Pioneer. And finally, I'm going to touch on some of the ideas that we have for future work of the project. So before we get started, we just want to clarify what we mean when we discuss adding new features in this presentation. Because adding new features is a really broad term. It can refer to something as simple as just adding a navigation menu bar to a UI, or it could be something as significant as making a fundamental change to the application's architecture. And these are the kind of changes we want you to keep in mind throughout this presentation. Specifically, when we refer to adding new features, we are referring to an organization that has a monolith, and they want to add the new features that are required to migrate to a microservices architecture. And to get a better understanding of the challenges facing an organization that wishes to make such an architectural change, we'd like to introduce you to our hypothetical company called Harvest Delivery. Harvest Delivery is a mid-sized retailer that provides an online grocery shopping service. And in this scenario, Harvest Delivery has grown to a size which means they're starting to see a strain on their current monolithic architecture. Some of the strains that they're starting to see with their monolith come from the fact that they have tightly coupled code. And in this situation, when a change is made to one part of the code base, multiple other components also need to be updated. This can slow development, and it can lead to the creation of multiple bugs that are really difficult to track down. Also, Harvest Delivery is seeing increased traffic, and they would like the ability to horizontally scale some of their application components in an individual manner. And this just isn't possible with a monolith. Finally, Harvest Delivery is experiencing issues with availability. With a current monolith, any bug that causes one of the logical components to fail, for example, the form that's required to register new users, will cause the entire application to be taken down offline. Extracting some of the application components into microservices can help keep such outages isolated. And it means that only users attempting to use the affected microservice will be impacted. So because of these challenges, Harvest Delivery wishes to extract some of their logical components out of the monolith into separate microservices. Let's say Harvest Delivery wants to add 3 microservices to their application, which are called a shopping cart, a payment processing, and a live customer service chat function. Now, this type of migration is commonly performed by organizations and is referred to as the strangler fig pattern, which is a term that was coined by Martin Fowler. Now, making these kind of organizational changes aren't going to be straightforward. It's actually going to be a lot of work for the development team, and it's going to be made all the more challenging because there are some other requirements that they need to meet. The most important of which is that they need to minimize the amount of time that the Harvest Delivery webpage is offline. And this is because downtime can cause a loss in revenue and it can cause damage to the company's reputation. Also, the development team doesn't want to roll out any of the new microservices to 100% of their users straight away. They want to have the ability to roll out a microservice to a specified subset of users, say 10% of their user base. Then they want to see how that microservice performs in production before gradually rolling the microservice out to an increasing number of users. Finally, Harvest Delivery is going to have 3 different teams developing each of the microservices that they're adding to their application. So they want the ability to control the rollout of these 3 microservices in an independent manner. So a challenge that all teams have to face when they're adding new features to an application is how to deploy the updated code. And the problem is that the deployment process can be time-consuming and it can be error-prone. And in the worst-case scenario, an issue in deployment can cause application downtime. And as we've discussed, that's something that Harvest Delivery really wants to avoid. Now, there are a wide variety of deployment approaches used by different companies. But if we look at either end of the spectrum, we can generalize one deployment approach as being slow but safe. And in this deployment pipeline, multiple integration tests are performed. The advantage of this pipeline is that it minimizes the risk of any issues arising in production. But the disadvantage is that it can be really slow. Performing this kind of deployment approach can take anything from a few minutes to a few hours. And for development teams that deploy multiple times every day, this type of approach can be a real bottleneck to development. The other end of the spectrum is a quick but risky deployment approach. And this pipeline can involve little or even no integration tests. The advantage is this pipeline enables teams to work in a highly agile manner, but the disadvantage is that it increases the likelihood that bugs will occur in production. Now, both of these deployment approaches have disadvantages, and it would be really beneficial if an organization had a way of managing the rollout of new features from within the deployed application itself. This would mean that teams employing the slow but safe deployment approach could save time by minimizing the number of times their pipeline would need to be run. And for teams using the quick but risky approach, they would benefit from having the ability to switch off a feature that was causing a problem in the deployed application. So now that we've looked at some of the challenges facing a team that's adding microservices to their application, Jimmy is going to discuss some of the potential solutions.
Thank you, Laura. So there are many deployment strategies for migrating from monolith to microservices. One reasonable fit for the Harvest Delivery use case is the Canary Deployment strategy, and we will go more in depth in the next few slides. Canary Deployment is where you have your original deployment, which is monolith only, and your new deployment, monolith and microservice, run side by side simultaneously. A load balancer will allow you to configure the routing of traffic from the public internet. Now, initially, 95% of traffic is directed to the original deployment, and 5% gets sent to the new deployment or the Canary deployment. And that's because you don't want all of your initial user base to be exposed to the Canary deployment, because you're not sure if there's going to be some bugs or issues with that deployment. But as the engineering team gains confidence in the Canary deployment, because it's been running for a while without some significant issues, they will start routing traffic more and more to the Canary until it receives 100% of all traffic. Let's examine how Harvest might actually use this deployment strategy to extract out 3 microservices from their monolith. So one option is to extract and deploy these microservices sequentially. And we'll call these 3 microservices A, B, and C for convenience. So initially, the original deployment would be monolith only, and the Canary deployment would be the partially extracted monolith and extracted microservice A. And 95% of traffic gets directed to the original, while 5% gets directed to the Canary. As time passes, the engineering team gains confidence in the Canary deployment, and now monolith and microservice A will be the new original deployment for the application. Now they'll repeat this process sequentially to extract out microservice B and also microservice C. Now we have an application with a partially migrated monolith and 3 extracted microservices. This deployment strategy, however, is not very agile for certain rollback cases if a microservice were to go down. Let's examine how the engineering team might respond to some of these situations when certain microservices have issues. So let's say microservice C were to experience issues. This will force the engineering team to roll back microservice C in their deployment. Ideally, they need a rollback version where it's just monolith and microservice A and B. Luckily, they could just switch back to the previous version because that was already deployed previously. So it's simple for that case. However, what if microservice A were to break? In that case, they would want to roll back to a version where it was monolith, but only microservice B and C. But that version was never created because every previous version had a microservice A due to the sequential nature of the deployment. So at this point, they have 2 options. They must either refactor the application code so that it only has microservice B and C, and that takes time and engineering effort, and they want a quick rollback. So more likely, if they do not have time to spin up that version, they would have to roll back all the way to the original monolith, and that's the only one that does not have the defective microservice A. However, there was nothing wrong with microservice B and C, and now you're just excluding them from active deployment, and you're missing out on valuable monitoring data. So this approach clearly lacks granularity of control for individually managing the active states of the microservices because they're all coupled together to the sequential nature of the deployment. So a naive solution to this would be to have every combination of microservice A, B, and C created beforehand. So that, let's say microservice A were now to go down, in this case. So microservice A were to go down. In this case, the engineering team could simply redirect to a pre-deployed version of monolith plus microservice B and C, as shown here. So this approach does cover granularity of control, but this would clearly be very inefficient to account for every combination, especially as more microservices are extracted. And to give further perspective, with 4 microservices, it would require a total of 15 deployments to account for every combination. So we can see there are many downsides to using this deployment approach for Harvest. While it does have percentage rollout, one immediate downside is the complexity coming from introducing additional infrastructure to your existing application, like the load balancer and all the extra deployment environments. In addition, the first option, which was sequential deployment, that did not allow for granular control. The second option was to pre-deploy all combination of microservices to allow for granular control, but that easily becomes infeasible. To address these issues, there should be a strategy in which the application code is engineered to handle the microservice switch rather than the load balancer. Now we introduce the concept of feature flags as an alternative solution to Canary deployment. This design pattern solves the previously mentioned problems because first of all, it allows you to independently toggle states of multiple flags, allowing for granularity of control. And each flag can be thought of representing the active state of one microservice. So flag A could represent the active state of microservice A. And this toggling can be done without deployment downtime, which will be later explained. In addition, this deployment strategy of feature flags minimizes interference with its existing infrastructure because, as we've seen, Canary deployment is a solution at the infrastructure level. Feature flags is a solution at the application code level. It only requires embedding an SDK into the existing code base without the need for an extra environment or load balancer. Finally, it still has the benefits of percentage rollout, and this can be adjusted through a UI rather than being configured through a load balancer. So to give a quick high-level overview of how it works, Pretend you have your monolith and your microservice extracted from that monolith. Initially, a request comes in from the internet. The app will handle that request, and it will handle it by referencing an SDK. This SDK will check for whether or not a flag is toggled on, and this flag would represent the active state of microservice A. So let's say the flag is toggled on. The app referencing the SDK will now route the request to microservice A. If the flag is toggled off, it will execute internal monolith code as represented by service A. To further emphasize the efficiency and convenience of feature flags, let's go back to the example where microservice A went down. Now on the left, the engineer only needs to toggle off the flag corresponding to microservice A. And let's say microservice A went down, so the engineer only needs to toggle it off. The SDK will be notified of the change so that future requests, instead of going to microservice A, will now route to service A, the internal monolith code instead. And especially important to note that this will not affect the activity of other microservices. To go more in depth as to what a feature flag is, it can be thought of as a key and a Boolean value, like a key value pair in a dictionary data structure. They are used in the code base as an if statement where there are two possible choices, and the Boolean value of the flag determines the flow control. So as you can see, the get feature method is passed in a key name, which can be thought of as the active state of microservice A. And if that returns true, we execute the new feature, which would be routing the request to microservice A. Else we execute the original code, which can be thought of as the internal monolith code. Now let's talk about the options that a company has if they wanted to adopt this workflow. They first have the option of creating and maintaining their own feature flag rule set. This carries the obvious overhead costs of the time and engineering manpower required to test and build a solution from scratch. Another option is to use third-party solutions. Proprietary software include Launch and CloudBees, while open source software include Feature Hub and Unleash. Let's examine these two sets of options in more depth and compare them with our solution. For a small to medium-sized company like Harvest, it's especially important to consider accessibility or ease of setting up because Harvest has a small engineering team, and also affordability because they are on a tight budget. Enterprise solutions such as Launch Darkly are closed source, come at a monetary cost to the company using them. Typically, these solutions provide far more features and require far more configuration than company require for the purpose of introducing new microservices. So that's Launch Darkly, and solutions such as Feature Hub, while open source and thus flexible, still offer a more complex set of features. This complexity requires additional time and effort to configure appropriately. Furthermore, the complex code base may be more difficult to modify for Harvest's custom needs. All of these considerations led us to develop Pioneer, which fits the use case of Harvest the best. Elizabeth will now present a more in-depth look on Pioneer.
Thanks, Jimmy. So now I'm going to discuss the details of our feature flag management tool, Pioneer. First, I'm going to introduce Pioneer, and we'll take a look at Pioneer's system architecture. Next, we're going to go a bit deeper and dive into each element of Pioneer's architecture to discuss the role that each component plays. Finally, we'll briefly discuss out-of-the-box usage of Pioneer. Afterwards, Kyle is going to take over and dive a bit deeper into the engineering decisions that we were challenged with when building Pioneer. Pioneer is a self-hosted, open source feature flag management tool. It's specifically intended for small to medium-sized organizations that are looking to transition from a monolith to a microservices architecture. Pioneer enables users to roll out individual microservices to a specified subset of users without the need for extensive configuration or additional infrastructure, such as a load balancer. You've heard us mention several times already that Pioneer is a self-hosted application. Let's briefly touch on the benefits that this affords Pioneer's users. Firstly, it means that the user can deploy Pioneer on their infrastructure of choice. whether that's on their own AWS VPC, a DigitalOcean droplet, or their own on-prem server. Distributing Pioneer as an open source and self-hosted application also means that users of Pioneer can fully adapt the application to their own unique needs, increasing flexibility. If the out-of-the-box configuration isn't a match for a user's requirements, they have the freedom to change whatever isn't working for them, or to add whatever components might suit them better. For example, if necessary, users can spin up additional instances of Scout or add a cache. We're now going to go over Pioneer's architecture from a high level. Pioneer is composed of multiple components called Compass, Nats Jetstream, and Scout. All of these components are run in a Docker network. I'd like to point out here in this diagram that Nats is a third-party tool. Compass is a React application built by the Pioneer team, and it serves as the dashboard for flag management. Scout is a Node.js application also built by the Pioneer team, and it serves as the distributor of flag data. Pioneer communicates with a user's application via a Pioneer SDK, which is embedded within the user application's code base. Let's now take a look at each of the components and the role that they play. Compass is Pioneer's primary application for managing feature flags. The front end of the application provides a user interface that allows users to view, create, update, and delete feature flags. Each flag has a title, an optional description, an assigned rollout percentage, and may be toggled on or off with a single click. Changes made to a flag will be published to Nats and received by Scout. Once the updated flag data is pushed out to connected SDK clients by Scout, the application's behavior will change to reflect the update. No redeployment is necessary. All that's needed to turn a new service on or off or update its current rollout percentage happens right here on the Compass dashboard. You may recall that when Jimmy spoke about using Canary deployments as an alternate strategy to roll out new features, a load balancer was required in order to direct the appropriate percentage of users to a new feature. When using Pioneer to introduce new features or services, there's no load balancer required. A feature flag's current rollout percentage is set as an attribute of the flag and is transmitted to connected SDK clients along with all other flag data. The SDK code includes the necessary logic to serve a particular feature to the percentage of users specified for that flag. Users may also use the Compass dashboard to view event logs regarding a flag's history. All updates made to a flag are preserved here for future reference. Under the Account tab of the Compass dashboard, users can view and manage the valid SDK key needed to connect SDKs as clients of Scout. Users can also choose to invalidate the current SDK key and generate a new one. Next, we're going to discuss the role that Nats Jetstream plays in transmitting feature flag data from Compass to Scout. But first, what is it? Nats Jetstream is a third-party open source message streaming service. Nats is lightweight and easy to get started with. Pioneer utilizes a Nats Jetstream server to facilitate communication between the Compass and Scout servers due to its ability to provide asynchronous, fault-tolerant messaging with guaranteed delivery. And Kyle's going to talk a little bit more about why we chose Nats specifically in a moment. Nats offers a few different messaging patterns. The pattern used for Pioneer is a publish-subscribe messaging pattern. When communicating via a publish-subscribe pattern, the subscriber acknowledges receipt of a message, but it's not expected to reply. And this is a perfect fit for our use case, in which Compass publishes updated feature flag data to NATS, and NATS stores the most recently published data in memory until the subscriber, Scout, acknowledges receipt of the data. Scout is a daemon that the Pioneer team built to act as the interface between Compass and the SDK embedded in a client's application. You can think of Scout as being the distributor of flag data. A persistent HTTP connection is formed between Scout and SDK clients. It is through this HTTP connection that Scout sends feature flag data as a server sent event, also called SSE. Pioneer currently offers server-side SDKs in 3 languages: Node.js, Ruby, and Golang. The user should install the appropriate SDK in their application code. And after doing so, the SDK can request to connect to Scout as an SSE client by providing Scout's server address and a valid SDK key. The SDK will then automatically receive feature flag updates each time a change is made via the Compass dashboard. The SDK stores the current feature flag data in memory and uses it to evaluate flags. All 3 of our SDKs also integrate with Google Analytics to aid users in collecting analytics events related to their new features. And we're going to discuss now how to get started quickly with Pioneer out of the box. First, Pioneer should be cloned from the GitHub repository, and then the user should navigate into the Pioneer directory. Next, the user should run Docker compose up. Now all components of Pioneer's architecture will be running. Kyle will discuss the logic behind why we chose to use Docker in the next portion of the presentation. As discussed previously, once a user has Pioneer up and running, they can create and modify feature flags using the Compass dashboard. Each time a change is made via Compass, the updated flag data is transmitted from Pioneer to the user application. Compass first publishes the updated flag data to NATS, and Scout, which serves as a subscriber to NATS, will then receive and acknowledge the message and distribute the updated flag data to SDK clients via SSE. You can see that changes made on the Compass dashboard are enough to influence your deployed application's behavior in real time. Granular control over the rollout of new microservices is just a click away, allowing engineering teams to avoid the lengthy and error-prone process of redeployment when changes need to be made. Note that in order to evaluate feature flags in a user's code, the user will need to install the appropriate SDK in their code base. This can be done with a single command. And on this slide, we see examples of the SDK installation command for each of our 3 SDKs. Within a user's application, the feature flags are evaluated within a conditional statement in order to determine the flow of code execution. Remember, feature flags are evaluated at the code level. There's no need for a load balancer or an additional deployed environment when using feature flags. Let's harken back to our harvest delivery hypothetical. One of the logical components that harvest delivery plans to extract out into a microservice is their payment processor. Here in the code example on this slide, we see what a conditional statement evaluating the payment processor flag might look like in harvest delivery's code base. The payment processor flag could be toggled on, toggled off, or have its rollout percentage updated, all without any changes being made to this code. There's no redeployment or additional engineering work necessary in order to see the change reflected in the behavior of the application. Because feature flags are controlled in such a granular manner, Any changes made to the status of the payment processor flag will not impact any other feature flags, such as a flag for an inventory catalog, for example. It's really as simple as that. And now I'm going to pass things over to Kyle, and he will be discussing the engineering decisions and technical challenges that we dealt with while building Pioneer.
Thanks, Liz. While building Pioneer, there were several key design decisions that we made, which involved careful consideration of their benefits and trade-offs. I'll go over those decisions now. The largest implementation decisions we'll take a look at had to do with the following questions. First, how to communicate feature flag data from Pioneer to users' applications. Next, whether to use direct communication between application components or a message broker. Also, how to effectively design server-side SDKs that can implement gradual feature releases. Additionally, how to format feature flag data for transmission. And lastly, how to best ensure cross-platform performance and flexibility. When designing Pioneer, we thought about how to communicate feature flag data between Scout and connected SDKs in users' applications. We considered several options for how to best do this. First, we considered WebSockets, but we found that they were not the best fit. WebSockets provide a persistent connection between a client and server. However, they're intended for bidirectional communication. In our case, we only needed to communicate flag updates in a unidirectional manner from Scout to connected SDKs. Polling was another option we considered. This involves periodically sending an HTTP request to a server to check for new data. However, this approach would not provide the user application with updated flag data in real time and would result in unnecessary network traffic. Next, we thought about webhooks, which are event-driven, unlike polling. You can think of webhooks as being automated messages that are sent when something happens. However, using webhooks to provide updates to the user application would require that the user's application server expose an additional endpoint for HTTP requests to be sent to. We were looking for a solution that would send updates in an event-driven manner without interfering with the user's application. We settled on using server-sent events to provide flag data updates to the SDK. SSE connections are persistent HTTP connections over which the server can send data. The server-sent events model of communication means that when something happens on the server, updates will automatically be sent to all connected SSE clients. SSE allows for near real-time unidirectional communication from Scout to connected SDKs. One additional consideration we had to make after deciding to work with SSE connections between Scout and the SDKs was that of security. How tightly did we want to lock down the ability to open an SSE connection with Scout to request and receive the organization's feature flag data? On one hand, we could leave the connections totally open. Any SDK could connect to Scout provided they had the correct endpoint to send a request to. This would make the integration of SDKs into the user's application quite easy. The only SDK configuration needed would be to embed Scout's address. Then the application would be able to request and receive rule sets anytime it was fired up. However, this would mean loosening security protocols on Scout to make the flag data more accessible. With no extra steps for authorization, a malicious party could open an SSE connection with Scout. Then, just like any legitimate SDK, they could also start receiving flag data. On the other hand, we could add additional security to Scout to lock down SSE connections more tightly. If we added a form of authorization, the connecting SDK would have to provide a valid key of some kind to be cleared prior to obtaining any flag data. This would provide an additional layer of security between an incoming connection to Scout and the organization's flag data. However, this would mean additional configuration for the user, as they would then have to integrate and manage the keys for authorization. It would also mean additional complexity for Pioneer having to generate, manage, and validate these keys. Ultimately, we chose to authorize all SDKs requesting to connect to Scout as an SSE client. This authorization will prevent malicious agents from gaining access to feature flag data. SDK clients initiate an SSE connection with Scout by sending an HTTP request to Scout's /features endpoint. Before serving feature flag data provided by Compass, Scout will verify that the SDK attempting to connect has provided a valid SDK key in the authorization header of the request. If the SDK key is deemed valid, Scout will open the SSE connection. It will then request the full rule set from Compass through NATS, and once received, transmit feature flag data back to the SDK. Subsequent updates will then be sent to the authorized SDKs via the SSE connection. In the end, we decided that the additional complexity of managing SDK key generation and validation was well worth the extra layer of security for the end user's data. With the line of communication in place that would transmit changes to flag data in near real time from Compass down to the SDKs embedded in the user's application, we could then focus on how we could build the server-side SDKs to make them as easy to integrate and intuitive to use as possible, while giving them the capabilities necessary for our use case, namely the ability to implement percentage-based rollouts. As we've previously discussed, solutions such as Canary Deployment are at the infrastructure level and use a load balancer to determine the percentage of users receiving the new feature, whereas feature flags function at the application level. With Pioneer, the logic of the percentage rollout strategy is handled by the SDK in the user's application code. To determine if an individual user, such as a harvest delivery customer, should receive the feature flag rule, the Pioneer SDK requires some context about the user. This context is simply a unique identifier assigned to an application user. In our hypothetical, you can think of this user as one of Harvest Delivery's customers, logging into their service to do some shopping, and their context might be their customer ID. To make use of the client context and the percentage rollout of the flag, the SDK client must be passed this context using a built-in method. This will signal that all flags should be evaluated using the provided user's context. When the feature flag is evaluated, the user context is then passed into a hashing algorithm we created, which will determine whether the specific user context falls within the associated rollout percentage for that flag. If the context falls within the percentage, the flag will evaluate to true, and presumably, the client will be routed to the microservice. Otherwise, it will evaluate to false, and they will be routed to the monolith service. While the inclusion of this strategy does add complexity to the integration of the SDK, we felt that the added complexity was minimal, and the ability to route percentages of users to a microservice was a worthwhile trade-off. Now, after deciding how to transmit updated flag data, we needed to decide what the format of these messages should be. Having settled on sending the rule sets as JSON objects, we wondered whether sending the whole rule set would provide any advantages over sending only updated sections of the rule set. We decided that Pioneer should publish the entire flag data rule set each time an update to a flag has been made. We also considered sending only the data related to the flag that was updated in order to reduce the size of the data being transmitted, but this came with its own considerations. The biggest drawback of transmitting flag updates in a piecemeal manner is that an SDK could miss a flag data update from Scout due to network issues impacting the SSE connection. This would result in an SDK evaluating flags using outdated feature flag data, and the discrepancy would persist until the next change was made to that particular flag. In order to ensure that all SDKs have the most up-to-date flag data at all times, we decided to transmit the whole rule set. And because Pioneer is intended for small to mid-sized organizations, we reasoned that the size of data being transmitted was acceptable. For example, a rule set with 100 distinct flags has a size of only about 20 kilobytes, which should be manageable for modern networks. Lastly, let's go over how we answered the question of how to best ensure cross-platform performance and flexibility. As we noted previously when discussing Pioneer's architecture, the main components, NATS, Scout, and Compass, are each in their own Docker container. Together, they run in a Docker network. We chose to Dockerize Pioneer because containerization falls in line with the flexibility and control provided to users by offering Pioneer as a self-hosted service. Regardless of where users deploy Pioneer, the behavior of the application will remain consistent across different platforms without the need for additional configuration. So, now that we have an understanding of what decisions were involved in making Pioneer what it is today, we can think about how we can continue evolving Pioneer as we move forward. Laura will now bring us through a few ideas the team has about how we might do so.
Thank you, Kyle. So currently with Pioneer, a single instance of Pioneer can only support a single application. So in the future, Pioneer could be expanded to support multiple applications by allowing for multiple distinct rule sets. Additionally, currently, the rollout strategy offered by Pioneer is just a simple percentage rollout. Additional rollout strategies that may be developed in the future could identify users internal to the organization, a predetermined group of beta testers, or a particular segment of the market. And this would allow for more tailored feedback on the performance of an added microservice. The last item for future development is flag expiration. So Pioneer is meant to be used for a transition to adding a new microservice. The conditional logic related to a feature flag should not live in the user's application's codebase indefinitely. Allowing developers to set an expiration date on a feature flag would assist in defining a clear testing or rollout window for adding this new feature or microservice. So this is our team. Thank you so much for joining us today. If you'd like to get any more information on our project, you can visit our case study for a detailed write-up or visit our GitHub repository. And we'd now like to open up the floor to any questions.
Okay, we have a first question from Brandon. Does Pioneer handle updating a microservice? If so, how would that work?
I can take that one. So the idea behind Pioneer is that you have to actually have the update already deployed to your code. So you have to have the two switches, the if-else statement already embedded in the code. And the Pioneer allows you to toggle between those two states. But if you have to update a microservice in and of itself, you still have to redeploy it.
Okay, so next question. Mark asks, what were the challenges you faced with setting up container-to-container communication?
Yeah, I can answer that one. So there is a fair amount of configuration involved when you're running things within a Docker network. It's actually not too bad. One of the decisions that we made was to extract some of the variables into a .env file. And this meant it would provide just a single place where if somebody was modifying the application to their own need, to their own use, they could just modify the env file rather than having to go through the application, like all different parts of Pioneer components and finding all the places that they had to kind of change those Docker configurations. So it actually wasn't too much of a challenge in the end. It's just kind of normal things that are associated with working with Docker.
Next question. How did you end up choosing feature flags as your project topic?
If nobody else wants to jump in, we actually discussed like quite a few different ideas. I think we ended up like each of us coming up with a different idea for a project topic, and feature flags just sounded like a really fun, interesting thing to work on. There hadn't really been any other capstone projects in this space previously. So we thought it would be like a really interesting space to start working in.
Okay. Lena says, amazing project pioneer team. And what was your favorite challenge working through this project? I guess that can be a question for everyone.
I don't know if the rest of my team are having issues with audio, but I guess I'll go first. Yeah, there were loads of challenges working with this project, to be honest. I don't think that there was like one individual component that was like really straightforward. Each component had like a different challenge associated with it. And also we're a very distributed team. Like between myself and Kyle, there's like a 6-hour time difference. So that definitely introduced some like novel challenges that it was really great to get experience with working in such a distributed team.
Yeah, personally, I worked on the SDK part, so it was an interesting challenge trying to get the percentage rollouts working, as I was dealing with a really nested set of modules. These modules all had to talk with each other in order to get the parts of the SDK working together. That was a fun challenge.
And I'll go ahead and echo Laura's answer here. I think one of the biggest challenges in the project itself was kind of like the work around it and learning to work as a team, functioning asynchronously across, 4 different time zones, which brought its own challenges.
Okay, next question. Mark asks, would there be problems if you had a proxy like Nginx for that communication?
Not sure, Mark, if you want to follow up the clarification.
Yeah, he's asking about
communication.
container to container communication. That was his previous question. So what were the challenges you faced with setting up container to container communication? And then the follow-up question is, would there be problems if you had a proxy like Nginx for that communication?
Well, we envisage that all of the Docker containers running in a Docker network would actually be running like on the same server. So we don't kind of envisage that situation where you would have a proxy in between those kind of microservices to communicate with one another. If you did do that, it would involve more configuration than we have out of the box. It is something that's possible, but it's not something that we've kind of accommodated for in the development of Pioneer.
Okay, Graham asks, does the Compass UI handle collaboration? For example, if I'm working with my team and I host my Docker containers publicly, does it provide any form of authentication to prevent anyone with the address from accessing the UI?
No, it doesn't, simply. I mean, because it's supposed to be like self-hosted, the idea is that only people who have the access to that address and can access the UI, like that's kind of the only security we've got in terms of the UI collaboration, really.
Okay, really great job, guys. And I'm sure you covered this, but I missed. Where does the code that determines which server's traffic gets sent to live? In other words, where in a Pioneer user's architecture does the 5% of traffic get routed one way and the 95% get routed the other way?
I could answer that. So the Pioneer user has a backend architecture, and they might run on a framework like Express. So if you use Express, or if you just created a simple backend, you have these routes like app.get or app.post, and that's where the app handles the requests from the internet. So that's where the user for Pioneer, the Pioneer user embeds an SDK in there. And that's where you put your if-else statement, and that's where the traffic gets routed one way or the next. Hopefully that answers your question.
And once again, great job on the project. I'm curious to know how you divided up the project tasks. Did each one of you have separate areas of the code base to control, and or did you work in collaboration across the code base?
So I think the short answer is we all kind of worked on everything. When we were first starting the project, I think we all initially took a chunk and we did our code spikes, tested things out. And then once we were ready to move on and start prototyping and connecting all of the dots, we all kind of worked on the pieces and stages together so that we could all become more familiar with the operation and how everything was functioning.
Yeah, I'd also like to mention that the pairwise coding, I think Kyle and I did a lot of pairwise coding. I felt like I got a boost of productivity from that. So that was also a pretty helpful collaboration strategy in our team.
Yeah, I'll echo that. Jimmy and I did a lot of pair coding, and we did some like even larger group sessions where all four of us would come in if there was like one really core piece, you know, for like how Scout was functioning, as that's, you know, the distributor of all the flag data. We would all kind of get together and just work through a couple of the core pieces if there were any issues with it, and that proved pretty helpful in getting stuff done, but also I think helping us all kind of understand how everything was working and fitting together.
Okay, awesome. So it seems like there are no more questions. So any final words?
Thank you very much for everybody who joined us today. We appreciate it.
Thank you all
Absolutely.
for joining. Your questions and feedback are great. And apologies for any technical difficulties. Thanks for bearing with us.
Yeah, something was bound to go wrong, but yeah, thanks for your patience and thanks for your attention. We really appreciate it.
Okay, excellent work.